Hi, welcome back to CS170. I'm going to try to run through the rest of the content for chapter 22 in this lecture. So let's see how far we can go. So the next point is this idea of the universality principle. There's not really like much to the idea. It's just basically saying that all of the computers, like in terms that you can relate to, maybe looking at between like a Mac versus like a regular PC. There's all kinds of different computers with different types of hardware configuration, different types of um, software on top of it. But basically, there's like this idea of universality that says that that uh, one computer can do what another computer can do, essentially, right? And so the difference will actually play out more just in terms of how powerful is the hardware, but the process itself, what it actually does, um, uh, one can do the other. Okay, so like we talked about earlier in the class, we talked about like how computer chips, they go out into memory, they might do certain very simple operations within its CPU, and then it's shooting it out back to memory. And then there's all these other processes, whether it goes out to the monitor or it goes out to, some off-site storage or something like that. But at the lowest level, like all the computers would have some similar types of functionality. Okay, so this is a key point here, right? Computer using simple instructions can simulate another computer. And that's the universality principle, okay? So these are the instructions, and it alludes to chapter 9. You remember we were talking about this at the lowest level, so you can, add two numbers, subtract them, you do these basic instructions, you're loading up, storing it, stuff like that. So these are basic instructions that all computers at the lowest level would be able to do. Okay, so if all the computers are basically doing the same thing, then, as I say, the hardware or the power, which translates into speed, is the difference, right? So basically, it's just saying, well, okay, you can simulate the other computer, but maybe you're doing it more slowly. But the output should be the same, right? So if this computer does 1 + 1, the other computer does 1 + 1, you should get the same result, right? Just that one might do it a lot slower or a lot faster, depending on how you look at it. Okay, so same but different. Okay, so there's so different things in terms of like the software that sits on top of it. So it's like the levels of abstraction, right? So there's different types of things that will sit on top of that basic computational power that you can, depending on what you're trying to achieve. Maybe you're trying to achieve a very user-friendly type of computer. You don't want people to be changing things underneath. You just want to say, oh, like, I hit a button and it does this or whatever, right? Versus like maybe another computer, you want to include all kinds of options that people can go in there and customize it to whichever way they want. Maybe focus more on a particular area that they're interested in, whatever it may be. So these are just like different layers of abstraction that they put on top of your raw computing power. Okay, so so that's why, it's talking about like, why do we need different copies of software to run on different platforms, right? Like I said, you guys can see this like most plainly in terms of like Mac versus regular PC. So there's differences just because of the target market, the type of people that they expect to use these computers, that might make the software better from their standpoint. Okay. Talking about outmoded computers, I mean, I think it's kind of self-explanatory. People kind of know this, where, if you're trying to run an older computer, you might say, oh, why does like the newest software runs slowly on the older machines? Um, so part of it is just, the new software might be looking at features that are not available in the old operating system, right, or the old software hardware, right? So, for example, like, a new computer might be looking at whatever version USB port to get some input. Might be you need certain drivers to run on certain printers, um, and you're just not able to run it because of X, Y, and Z, like it's old standard and whatnot. And so there's a lot of reasons why that might be the case. Um, Probably another case would be like in terms of like the memory or just the overall hardware setup, right? So older computers, maybe they were all set up to run like on one CPU, right? Instead of like these days, everything is running on generally multiple CPU. And there's a lot of things that maybe the particular address size is bigger, so you can get more information into one push versus like the older computer, right? So there's all kinds of reasons why new software is going to run much more slowly on the older machines. Okay. Okay. So from a computer science standpoint, they look at how a computer processes things, or in this case, an algorithm. Algorithm is just, as we talked about earlier in the class, a series of steps that the computer will follow to do something, right? Let's say you're doing your recipe to cook, to make a cake or something. The computer is processing its algorithm, and they want to measure, how efficient the algorithm is. Okay, the computer is the computer, the hardware is the hardware, right? But the software itself, it can be put in such a way that it can use that hardware in an efficient way or inefficient way. Okay, or just the nature of the problem may cause you to have a whole bunch of like computations. Okay, so they talk about the order of size n, right? So you have algorithms, you're going to process this, and it's going to be based on this size n, okay? So one of the more tricky algorithms that's harder for computers to deal with, like the number of computations as it scales up, it basically scales up exponentially. So those become more challenging for computers. Okay. So they have this one is the example is the shortest or cheapest route to tour n cities, right? You might know it as like the traveling salesman problem. Okay. And then these are in the category of what they call NP complete problems. And we have traveling salesman here. Okay. So basically you can picture it like all of here's the starting point, right? And then you can picture all these different cities here. And then all of these lines are the cost to travel between one city to the other city, right? So in this case, they're talking about distance, right? But it could be more combination of distance with the cost of, let's say, the gas you put in the car to travel, or if you're flying, the airline ticket or whatever. So, basically any sort of number that will, or weighting that will be applied on the path between one city to another city. And then you're trying to optimize, like if I want to hit all these different cities here, and let's say come back to here, what does that cost? And how do I find the optimal cost, right? So If you have something with only a few cities like that, you can say, oh, okay, that's easy. I can, just add up the numbers and then figure out, which is the best way to go. But you'll see in short order, like as you add more and more cities to the list, the number of combinations starts to exponentially grow until the point where it's like just a ginormous number of permutations to try to figure out what the weighting would be to come up with your optimal path. Okay. So yeah, and all of these points just explain what I was just saying. Objective, minimize the total distance traveled. Okay. So there's another term that they refer to on this. They call these problems intractable. Okay, and so, in short order, when you, let's say, put in the number of cities in the United States, you're going to get like a very large data set that is going to be very difficult for a user to be able to solve in a reasonable period of time. Okay. So, so this goes back to the original title of this chapter, talking about the limits of computer science, right? So certain types of calculations that will just take a very long period of time. Problem is non-computable, right? Just keeps on going forever and ever. Maybe at some point some of these things get addressed with things like quantum computing. Okay. But here's some particular topics that are just like very wide open to be able to try to solve. Computer vision, artificial intelligence, modeling complex systems like weather. Okay. So a lot of times when you look at like internet security, you get into things like doing factors like primes and stuff like that. So this is just an example of this, like trying to factor out this number. And this is a key point here, saying that, encryption is based on the fact that it's very difficult to factor these numbers. Again, like I said, when you look at quantum computing, these type of challenges will potentially be addressed, and then we'll have to figure out a new way to do encryption. Okay. But like I said, this kind of goes back to when we were looking at a few weeks ago or a couple of weeks ago, we were looking at encryption, public key and private key encryption. The encryption is based on being able to do factors or not do factors, right? So that's another situation here. Okay. So this is the last part of this lecture, talk about the halting problem. So this is, I alluded to earlier when we were talking about debugging. This is why it's hard to have a computer to be able to figure out how to debug your code. In some cases, it's very easy to figure out. But if you look at like all the possible ways that you can do have a bug in a program, it's not really possible to have a program to be able to debug another program for you or a piece of code for you. Okay. So here, this is the idea of whether essentially it goes into a infinite loop, right? So you remember we talked about infinite loop where I could potentially punch in something and it'll just keep on going forever. And it's hard for it to know that. So for example, you remember we did the for loop, right? So we did a for loop and you can say, well, for I equals, let's say 1, right? And then you keep on doing +1, it makes it keep on going up. And then you make the checker to say, oh, when it gets to 10, stop. Okay, well, that's fine. But what happens if, my starting number is like 10, like for I equals 10, and then I keep on going up. And then for some reason, I decide to set the loop to end at 9, right? Or actually, I should say it the other way. If the check is not checking something that is ever going to hit. So in this case, I'm saying if the check is greater than 9, it's going to keep on going forever, right? By the same token, I can change the, let's say the counter within the for loop again to keep it from ever reaching to a conclusion. Maybe every time it goes through, I keep on resetting that counter to a lower number, so it will never hit that maximum number. So those type of things, this is like the halting problem, okay? So the straightforward standard for loop that you see, yeah, it's going to return. It'll be true, and then it will halt, right? But in some cases, if you programmed it with a logic flaw, it will never return. And for the computer to be able to tell you upfront that is either going to halt or never halt is a problem that it cannot do right now, okay? So anyway, this is it for this week's chapter, chapter 22. If there's any questions, let me know. As I said in the first lecture for this week, if there's things that you want me to cover for the final, just let me know. I'll try to cut some more videos this week. And take a look at the textbook. The textbook covers all these different topics, probably in more depth than I just covered. And if you have any questions on any of those, let me know. Let me see here. So just remember, you got the Turing test, the evolution of computer intelligence, universality principle, the way that the work in a program or algorithm is computed, and this idea of NP complete problems. Okay. And with that, I'm going to wrap up, and good luck with your studies. Good luck with catching up on your quizzes that will be opened up later this week. Take a look at those exam 2 questions to help you study for the final. If there's any questions on that, send me an email. Like I said, I'll be grouping up your emails and allocating your extra credit later on this week. Okay, with that, it's been great having you for this semester, and good luck with the finals. Thank you.